we have already seen that you can represent a function as a Taylor series. So basically, when we started in the beginning, we saw that if you have f of x, if you have this function, it can be represented by this series, 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial uh, plus and so on and so forth up to x to power n, this, n factorial, which is the nth term, up to infinity. All right. So we can represent a function which is given here by e to power x as a series, that is Taylor series, and the specific word for that is actually not a Maclaurin series is a Taylor series, so we can specifically call it as a Maclaurin series, and you have it in your formula booklet, which is here. All right, this bit here. Anyway, what I want to show you here, back here, what I want to show you here is that if you have this exponential function, you can generate a series for a certain number of terms. All right. For example, when so suppose you have a series, maybe I need to, if you have a series representing this, then you can generate several polynomials that can estimate, that can approximate the original function. All right. And what you're seeing here is basically, let me start from the basic one here. So this series here is given by this series here is given by the sum, and we already discussed this. So this is f of x, the sum from n is equals to 0 to infinity of x to power n over n factorial. All right, and you can generate this for a given number of terms. You can generate it up to x cubed. You can generate it up to x to power 3 term. You can generate it up to x to power 4 term. Now, those are what are called Taylor polynomials. All right. So basically, what I have here is, if I can just start from the original function. So this function here, this function here is e to power x. So this is f of x is equals to e to power x. And if I generate a Taylor polynomial here, for example, this one here, that one. So this is the Taylor polynomial. All right. And we use that symbol to represent a Taylor polynomial. So whenever you see t sub n, that is a Taylor polynomial. That's what it means by a Taylor polynomial. So anyway, just go back to what I was trying to explain here. So if you increase the number of terms that you are using to approximate this, for example, if I have my series up to, the higher the value of the higher the number of terms that I'm using to, actually the higher the degree of the Taylor polynomial, the better the approximation. All right. So this is low degree, but this is a higher degree polynomial that I'm using. So I'm using more terms to kind of approximate this polynomial. All right. Anyway, I'll discuss this in details here. So consider a function f of x is equals to e to power x. The nth degree Maclaurin series for e to power x is given by this. That is up to the nth term. Now here, remember, we are using this words here. We are using nth degree polynomial. So that is t sub n, all right, which is given by that. So using the Maclaurin series for f of x equals to e to the power x, we can try to approximate the value of this function near x equals to 0. So what we mean by that is, coming back to our graph here, so this is a Maclaurin series about x equals to 0. So if we want to approximate, say you want to find the value of this function at this point here, we want to find the value of this function at, x is equal to, this is not drawn to scale anyway, but it's drawn to scale, but okay, let me try to put it somewhere there. So you want to approximate the value of e to the power 0.5 at x is equals to 0.5. All right. So we can try to approximate, use our Taylor polynomial to approximate the value of e to the power 0.5 because it's closer to 0. And the reason we're choosing a point close to 0 is because this is a Maclaurin series, centered about 0. Anyway, so we can use our Maclaurin series to approximate the value of this function at x is equals to 0.5. And we can try to find out how accurate the first few terms of the Maclaurin series are. Okay? All right. Just note that the exact value of e to the power 0.5, this is from my calculator, is equals to that. But, we are going to investigate and find out what happens if you have first degree polynomial, second degree polynomial, third degree polynomial, fourth degree polynomial. What happens when you have different degree polynomial, Taylor polynomials, when you're trying to approximate the value of a function? So let's start with a first degree Maclaurin polynomial, which is given by that. This is actually this one here. So this one, all right? So this is the polynomial that I'm using. And if you use that polynomial to find e to the power 0.5, it will be approximately equal to 1.5, which is an error of just over 9%. All right? Percentage error of just about 9%. And if we use a third degree polynomial, so third degree polynomial will be something like that. All right? So what you have here. So if you use the third degree polynomial, this will give us e to the power 0.5 as 1.6458333, which is only a 0.175% error. Now, if you use a fifth degree polynomial, a seventh degree polynomial, all right? If you use a seventh degree polynomial, then you end up with something like that, all right? So this one here. So this is a seventh degree polynomial, the one in pink. And this will approximate the value of e to the power 0.5 to, it will be correct to 5 decimal places. So this is correct to 5 decimal places, which is much, much better than whatever we had initially. So clearly we can see that as n increases, the Taylor polynomials approximates the function more accurately. All right. So the Taylor polynomials approximate the function more accurately as n increases. So as n increases more accurately. So, and you can see from the diagram that we have here, if I increase n n, you can see we are actually ending up with a better and better fit. All right. So if we denote Rn to be the error involved, so this is the error involved. So if we denote Rn to be the error involved, when using any Taylor polynomial to approximate a function, then f of x will be given by um, uh, uh, t sub n of x plus r sub n of x. So this is t sub n of x is the Taylor polynomial up to the nth degree polynomial. So and then r sub n is the error that arises from that approximation. So as n increases, the error decreases, and our Taylor polynomial becomes closer and closer to f of x, as you've seen from the diagram that I've shown you. All right, so we've seen that f of x is equals to t sub n of x plus r sub n of x, and you can write this equation this way. It's the same thing. Where this is the error. So that is the error. And the remainder is given by this formula, right? The remainder is given by this formula. Now, this is in your formula booklet. And this is called a Lagrange form of error term, all right? So Lagrange formula. Now, I just want to point out that whatever I have here is not exactly what, the notations that I've used here are different from what you have in your formula booklet. If you look in your formula booklet, what you have is that, all right, which is different from what I have. So in place of, I've used Z instead of C, but it all means the same thing. Anyway, so I'm going to carry on to explain this. The proof for the Lagrange form of error term is beyond your syllabus, but you just have to know how to use it. All right. Now, there are a few things that I want to mention. Z is between x, the point you're trying to approximate, and C, the point that you're using. I'll explain that when we'll be solving problems. It'll make more sense when we start solving problems and applying this. We have to pick what Z is. All right. Now, remember, Z will help us to determine the maximum error, and you can just do that by inspection. I'll explain that later on. Now, one most important thing is, although the Lagrange form cannot compute error exactly, it does provide an efficient and accurate way to find the maximum error, and I'll explain that. This will make more sense when we apply this in solving problems. So let's carry on to the first example. So example 1. Find an expression for the error term in approximating e to the power x by its second degree Maclaurin polynomial. All right, so what we have to do first of all here is we have to find the error term associated with a second degree polynomial. So the error term Rnx, and I'll use the one that I have in my notes. You can use the one that you have in a formula booklet, but just to be consistent, I'll stick with what I have in my notes. The formula is the same. The variables that I've used are the ones that are different, but the formula is exactly the same. So f n plus 1, the nth plus 1 derivative of f at z, x minus c to power n plus 1 over n plus 1 factorial. And this is exactly the same formula what you have here. All right. So they just want us to find an expression, which is fine. So we just have to find what these guys are. Now, so because we are final expression for the error term in approximating e to power x by its second degree Maclaurin series, so n is equals to 2. Those are some of the things that you need to identify. It's Maclaurin series, so which means that c is equals to 0. Okay. Yeah. And then, so we need to find the derivatives of f of x. We know that, you know, the nth plus 1 derivative of f of x, actually, before I write that down, let me just write this formula. So this will be r, because n is 2, so replace that with 2x, all right, because this is an expression. We're not finding a specific error. Now f, now n plus 1, that will be 2 plus 1 will be 3. So the third derivative of f at z is what we'll be looking for. And then we have x, which is just x to power 3, because c is 0. So x to power 2 plus 1, which is 3, over 3 factorial. All right. So I've just, you know, substituted what we have into this expression, into this equation. All right. Now, we know that, you know, f of x is equal to e to power x. So the third derivative of e to power x is just e to power x. So the third derivative of this guy will just be e to power x, which means that the value of the third derivative at z will just be e to power z. All right. So our expression will be r3x will be equal to e to power z x cubed over 3 factorial. All right. I write that properly. So e to power z x to power 3 over 3 factorial. All right, let's carry on. So the second part is give an upper bound to 4 decimal places on the error when using this approximation to find e to power 0.75. So now here, this means x is equals to 0.75. All right, this means x is equals to 0.75. All right, so you're going to find in part B, this is part B, we are going to find R3 at 0.75. So what I'm going to do is just to plug in this bits. So this will be e to power z 0.75 to power 3 over 3 factorial. Now we have to find z. Remember what we said initially. We have to pick what z is. Now, we know that z is between 0 and 0.75. All right? Not. Z is between x and c. All right? 0 and 0.75. Just remember that this is x and this is c. All right? Now, by inspection, there will be a larger error if z is equal to 0.75, because remember z is between 0 and 0.75. What you're interested here is to find the magnitude of the error, right? So what will be the error at most? The magnitude of error. So there will be a higher error because if you plug in, for example, 0 in place of z, then you'll have e to power 0, which is 1. Then you'll have a lower error, lower amount of error. But if you plug in something like, for example, 0.5, that will be in between. If you plug in 0.75, that will be a higher error that will end up with. So basically, we can say that by inspection, will be a larger error if z is equal to 0.75. So this is by inspection, very important, by inspection, all right? By inspection, then, all right, so let's carry on. So R3, 0.75. So the magnitude of error will be e to power 0.75, 0.75 to power 3. I need to write that properly. 0.75 to power 3 over 3 factorial. Now, if you plug that in your calculator, that will give you 0.1489. What that means, this means that this is the error at most, maximum error. So, at most error. So, the error let me just write it as the error is at most 0.1489. All right.